Hello, hello, everybody. Hello, good evening. How's everybody doing?
Attention, please.
That'll do it. How's everybody doing tonight? Come on. How's everybody doing? That, I don't know. Yeah, there we go. Yes, hello. I'm glad to see everybody. My name is Aaron. I am one of the hosts tonight. I have Caleb to my left and then Jasmine further along. We have Adam and Brian running the show. Tracy's here in the flesh. Michael and Erica and Sam are not here tonight, but then we have Thomas online. I don't have a joke, but I am delighted every month by the turnout for this event. It fills my heart to see everybody for me to have to tell people like, hey, I'll pull up some chairs for you. Like, that's a good thing. It's a good problem to have. How many first timers out here tonight? Wow, nice. A good crowd. A good bunch of you. And then for the veterans, you know the deal. We have to outdrink the rookies. But for the first timers, Caleb. For the first timers, you want to tell them what Astronomy on Tap is?
Yeah, certainly. So let's go ahead and do that. So so Astronomy on Tap, what on earth is this thing if you've never been here before? Well, Astronomy on Tap is a worldwide phenomenon. Yes, started in New York City in 2013, and it has spread like wildfire. And so all around the world, we have these Astronomy on Tap events where we invite scientists and other passionate astronomy tangential folks to describe kind of their perspectives on astronomical topics. And so what is it? Well, hold down. There we go. Well, it's interesting. For one thing, yes, we have very interesting talks. We always try and line up some good array of speakers and topics of which the speakers talk about for these events. Also, it is fun. Yes, we have a lot of fun. Isn't that right, folks? Yeah, okay, we have a lot of fun with this. And then not only is it fun, but it is also interactive, and that brings up a very important point. There will be a phone number on this screen, maybe. That screen? Okay, it'll be on this screen. Okay. For you to text questions for our speakers at the end of each of their talks. And not only that, but also during the talks, they will usually have a drinking word. So, yeah, be prepared to drink up, all right? Be responsible, though. Yes, please be responsible. Find drivers. Yeah, definitely drink safely, okay? So, anyway, and then not only that, at the end, we do have trivia, so do not run away at the end of the talks. There will be trivia. There will be prizes to win, which we have up here. I think we'll describe more of what those are when it is trivia time. Not only that, we do have merchandise over here for sale for recommended prices if you want some souvenirs to take home. And with that, I think I will go ahead and hand it back. Hand it to you, okay.
All right, so what's the schedule tonight? So first we're gonna start off with a song of ice and dust, or why we're sending a $40 million trash can to Jupiter, from Dr. Zachary Ulibarri. Then we're gonna do an intermission with the UTSA Astronomy Club's Astro in the News, which is hosted by me and Caleb. And then we're gonna end with Space Volcanoes from Dr. Alan Whittington. That should be interesting. And then after that, stick around and we're gonna have our trivia with amazing prizes. So thank you.
I see the. So I want everyone to at least note it down. We don't have a second laptop, but we have more slides. So text your questions to this number on screen. Don't be weird, but that number will come up later at the end of this end of the talk as well. But if you write it down now, you can. Oh, that's fine. Thank you, Caleb. But yeah, The number will come up at the end of the talk as well. You can text questions. You can write it down now so you can get your questions ready to go. And then Jasmine, do you want to introduce our speaker?
All right. So we have Dr. Zachary Ulibarri, who is a postdoctoral researcher at Cornell University, where he has the fancy pants title of 51 Pegasi B Fellow in Planetary Astronomy. We unfortunately won't have time at AOT to learn about his current work on vacuum-capable electrospray ionization mass spectrometers or about the time he rode his bicycle from Virginia to Oregon. However, we will have time to learn about his PhD work at the University of Colorado Boulder about trying to discover the speed limit of flyby spacecraft looking for alien bacteria. Proudly hailing from Albuquerque, New Mexico, he greatly misses the mountains, food, and sunshine of the great American Southwest, and he's happy to be here so he can remind you Texans that chili with an E is far superior to chili with an I. Woo.
Yeah. So as a lot of people know, we have a drinking word, which means when you hear the word, you say, and you take a drink. Zach, what is the drinking word?
I think we'll just go with moon, because I can like choose to throw that in there when I want to. So yeah, I think we'll just go with that. We'll see how it goes.
As we said, drink responsibly.
Oh. Actually, Control L to decide that. Oh, but that's now on the wrong screen. All right. All right, thanks again for having me. Once again, I'm Zachary Ulibarri, and so today we'll be talking about really a lot of the work that I did during my PhD at the University of Colorado. And to do that, we're going to start by talk about really a mission like this here. This is the Europa Clipper, which is shown here flying around Jupiter. And so let's get into that. Let's start talking about it. So we are going to start by talking about, of course, the most massive planet in our solar system with Jupiter. And what you find is that around it, there is a very small moon, which is called Europa. Oh, right, I forgot. Yeah, do the thing. And so Europa was so small that this was actually the best image we had of it for quite a long time. This image wasn't even available until the 60s. This is from the Pioneer spacecraft. But, of course, we have better imagery now, like this one from the Cassini spacecraft. So this shows you Europa, and you can see there's a lot of interesting surface features on this, right? It's composed largely of water ice, which is what the white structure is. But then you see there's other stuff. There are these red regions. And in particular, they form these cracks or streaks across the surface. You also have these kind of more muddled regions and chaos regions, these weird structures over here. But one of the things you might notice is that there's not really an awful lot of craters on this surface. It's actually pretty smooth. And that would seem to suggest that the moon is, the surface of it is actually very new. It's very fresh. Something is going in and refilling these craters as they are created, right? Compare this to Earth's moon. There's craters all over it. I chose it. I thought I actually did not realize how much I say the word moon. Yeah, anyway, so whatever. So, yes. But Europa's not the only game in town. Oh, sorry, I should say that despite being significantly smaller than the Earth, there's actually a little bit more water there. So compared to not any general, like the moon, which I don't think count. Oh, okay, whatever, fine. Anyways, it's actually smaller, but the point is that there's actually more water on Europa than there is on Earth. And so Earth, right, we have an ocean that covers like 75% of the surface with a maximum depth of 14 kilometers at the Marianas Trench, whereas Europa has a global ocean with an average depth of about 100 kilometers. So just stop and think about that for a second, like 100 kilometers of ocean straight down, and it covers the entire surface of the object. So there's actually more water there. And the important thing is that what you see in this cartoon here, this is from NASA JPL. There's a couple different versions of this cartoon, but the important thing is that we have pretty good reason to believe that this is what the structure looks like. You have, just like Earth, a metallic core surrounded by a rocky interior, and then this global ocean, again, with an average depth of about 100 kilometers. So an awful lot of water there. But the important thing is that we believe this ocean to be liquid water. So liquid water is, of course, vitally important for life here on Earth. We don't really think about it, but water is actually one of the weirdest chemicals in the universe, and that's like why it's so fundamentally important to life here on Earth, is because it has these really unique properties. It's just such a vital, integral part of our everyday life. We don't really ever stop to think about how weird it is. And the fact that there's liquid water here, which is so important for our own life, means that this is one of the best places in our own solar system that we could go and look if we wanted to find life somewhere else. But Europa is not the only game in town. If we look at this beautiful photo from the Cassini spacecraft of course, Saturn, the most photogenic of our planets, the eagle-eyed amongst you might be able to see there's a couple of other features here. Can people see them? Anyone? Oh, you saw the talk. You don't count. Okay, but anyways, well, whatever. Anyways, there's a little dot right there. That is Enceladus. And then there's another dot right there. That's Mimas. But no one cares about Mimas. And part of the reason is because Enceladus is really cool. Here's the black and white image showing the surface of the moon. And again, yeah, and you'll notice that there is an interesting dichotomy here, right? What's the dichotomy? Just shout it out. What's different here? Exactly, craters. On the north side of the object, there are an awful lot of craters, whereas on the south side, there aren't any. And there are these features here, which are called the tiger stripes, which you can see better right here. We call these the tiger stripes because they're shaped like stripes. But the important thing is that there is active plumes or geysers that are being ejected from these surface features. So this was, again, taken by the Cassini spacecraft. And this is showing these plumes that are being actively ejected from the surface of the object, or the moon. Oh, yes, thank you. Alas, I wasn't anticipating the microphone, but yeah, anyway, so we have these active plumes or geysers, and so these are spewing material out into space. But one of the cool things is that by flying through this plume, the scientists on the Cassini spacecraft were able to show that these plumes are coming directly from the subsurface ocean. So these plumes are not from the ice itself, they're actually from the ocean underneath. Which means that as you fly by this thing, you don't have to land. You can actually study the chemistry of the ocean just by flying by and sampling these these plume. And by using an instrument kind of like this, a couple different instruments, but one of which was called an impact ionization time-of-flight mass spectrometer, combined with some of the other instruments on the spacecraft, scientists were able to show that this is this water ice plumes. These are composed of icy dust grains. So like a millionth of a meter in diameter, tiny little dust grains composed of water ice from the subsurface ocean. And so you might have, this is another cartoon from NASA JPL. You might have something like this, or you definitely have something like this at Enceladus. You might have something similar going on at Europa. But even if these things don't exist, there's other mechanisms for there to be these ejection of these dust grains into the volume immediately surrounding the moon. So if you have these cosmic dust impacts, so dust grains are moving throughout the solar system all the time. Here at Earth, in our upper atmosphere, every day we get about 30 tons of dust grains that hit the upper atmosphere of Earth every single day. So just stop and think about that for a second. Imagine 30 tons of material in the form of little microscopic dust grains. It's an awful lot. It's happening all the time. These other objects throughout the solar system are no different. There are these interplanetary dust grains that are striking the surfaces all the time. But because they don't have atmospheres like we do, these dust grains can come down and reach the surface. And this is particularly important for objects that are coated in ice. Because for ice surfaces, you can actually get 1,000 times the original impactor in ejecta. So if you have an impactor of mass m, shown in red here, you can get several thousand m worth of material from the surface that are kicked up. So it's a very efficient process. One dust grain can produce 1,000 other dust grains. So if you were to look at the object, or look at Europa, this isn't really the full picture. This is. There are tremendous numbers of these dust grains on these ballistic trajectories, whether they're coming from plumes from the subsurface ocean or whether it's because dust grains are coming in, striking the surface, and then kicking up yet more dust. So this gives you a tremendous ability to study the chemistry of this object without even having to land. You can fly through this and study the chemistry. And so we're going to do this with the Europa Clipper. So this mission just launched in October. And on board, there is the SUDA instrument, the Surface Dust Analyzer, shown here. So this is the flying trash can. In flight, this here is a hinge, and this is a little lock here, and then this circular thing on the front is a door. And so what happens is in flight, in the vacuum of space, this lock will open, and the door will fly open, and then you have your trash can faced open that flies by, scoops up these dust grains, and can study the chemistry using this process that's called impact ionization, time of flight, mass spectrometry. So let's talk about that for a second. So again, here's our trash can. Here's the open surface. You have a couple of different grids which we use to measure certain quantities about the dust, like its charge, its velocity, stuff like that. But the important thing is that as the spacecraft goes flying by this object at several kilometers a second, typically they're flying by at around 5 kilometers a second for one of these flybys, the dust grains come in and they strike the bottom part of the trash can. Now, when you're flying at 5 kilometers a second, just stop and think about that. Imagine how long it would take you to drive 5 kilometers going down the highway, and imagine doing that in a single second. That's how fast the spacecraft is moving. There's an awful lot of energy in that. There's an awful lot of kinetic energy that this dust grain strikes the surface of this trash can with. And so this violent impact process creates what's called impact ionization, where the molecules come in, they strike the surface, and this violent impact rips off electrons and creates a positive charge in the molecules. And because of that, we can use these complex electric fields to focus them onto a target here, which is what these arcing lines are doing here. So the important thing is that the heavier particles travel slower. So we give everything the same kick, which means that the heaviest particles take longer to do this kind of trajectory than the lighter particles, right? If you kick a tennis ball, it's going to go really fast. If you kick a bowling ball, it's going to go really slow. The same thing is happening here. So they spread out in time according to their mass, because the heavier ones take longer to reach your detector. So by measuring the time, we measure the mass. And if we measure the mass, we measure something about the chemistry, right? If you know the mass of each of these molecules, you can say something about how it was probably put together. So that's what we're able to do here. We're able to measure the chemistry of these incoming ejecta particles when they hit the bottom of our trash can. So the question is can we use this to detect amino acids? So why amino acids? What are amino acids? Well, they encode your DNA. So all of life on Earth uses 20 amino acids. And it's what, like the different building blocks that encode your DNA and make you who you are. Some of them are really simple, like glycine here at mass 75, or alanine, which is here at mass 89. And then some of them are more complex, like histidine, which is at mass 156. The thing that's interesting is that abiotic processes like to make the simpler ones, like these two, glycine and alanine, whereas life likes to make both simple and complex ones, right? So if you have a system where you have like the building blocks that eventually that eventually makes these things, it really makes the simplest ones very commonly, whereas the more complicated ones it makes very, very rarely in an abiotic system, a system that doesn't have life. So if you look at an abiotic case, here are actual numbers from the Murchison meteorite. If you have something like complexity on the x-axis, which could be like mass, although it's not quite the same thing, but it's close enough for our purposes, what you see is that at the lower end, you have a lot of these really simple amino acids like glycine, and at the higher end, you have virtually none of the more complex ones. So, as I said, life here on Earth uses 20 amino acids to encode your DNA. There's actually thousands of possible amino acids, and in the Murchison meteorite, there are many hundreds of them that were detected. I think at least 800 amino acids were detected in the Murchison meteorite. But one of the interesting things is that out of these many thousands of possible ones, histidine was not detected at all. It's one of a number of amino acids that has never been detected in an abiotic inventory. It's only associated with life. It's only associated with biotic systems. And so, because life needs these things to survive, it ends up creating them. It makes them so that way it can do stuff like make your DNA and build new cells and do all that fancy stuff. So if you look at a biotic case, a system that has living organisms, that has biology, you get something that looks like this. It's a much flatter profile as opposed to this, where everything is stuck there down at the lower end. And if you want to see more about this, there's this really cool paper, which is Higgs and Pugers 2009, Thermodynamic Basis for Prebiotic Amino Acid Synthesis in the Nature of the First Genetic Code. Really cool. This is actually one of my favorite papers of all time. It's really great. Read it. It's a scorcher. Love it. So, again, impact ionization time of flight. So we put these on this flyby spacecraft. We impact the dust grains at several kilometers a second. It creates an impact plasma, this violent impact. The higher velocities, though, can produce greater molecular fragmentation, right? So if you're, now what happens if you go really, really fast? You're hitting this thing so hard. Does your complex organic chemistry, like your amino acid here, does it fragment into smaller pieces? And can you actually then figure out what the original parent molecule was when you're only getting now these fragments, these different small pieces? So let's ask a couple of scientific questions here that we want to answer. Does complex organic chemistry survive impact at typical flyby instrument velocities? Is there some critical breakup velocity? Is there a speed limit beyond which this fragmentation becomes really problematic and it becomes a lot more difficult to figure out what it is you're looking at? Can fragmentation products identify the parent? So if there is fragmentation, is that necessarily a bad thing? Can we actually use this to our advantage in some cases? And then lastly, what effect does the presence of water ice have? So again, these tend to be icy dust grains, especially around the moons, Europa and Enceladus. So what effect does the presence of water ice have there? So to answer this, we did a suite of experiments at the Colorado Dust Accelerator, which is shown here. This big object here is called a pelletron, which is kind of like a Van de Graaff generator, if you know what that is. The point is it gives you a really strong electric field. It gives you a really powerful potential, 2.4 megavolts of potential. So like, the power outlets right there, those are like 120 volts, right? The really high power transmission lines outside, there's like 120 kilovolts, I think. This is 2.4 million volts, so it's significantly higher than anything you will find outside. It's a really tremendous amount of potential. And so because of that, you can then accelerate dust grains down towards a bunch of detectors that we have in our big chambers down here. We can accelerate grains of up to perhaps a couple microns, so millionths of a meter is a micron, a couple millionths of a meter, at velocities of up to 100 kilometers a second. We typically shoot iron and aluminum, really things that are conductive. Those are kind of the workhorse dust grains. They fire very well. But in certain cases, we can also fire more exotic things like olivine, which is a mineral, or latex, which is a complex, plasticky type of thing, right? This is the like a system diagram. So here you have our pelletron. We accelerate things down this beam line. We have a lot of different detectors that we can use to tell you information about the dust grains as they go down. And then we have our big target chamber here at the back end. And what we can do then is we can wheel up big experiments either to the back of this chamber, or we can install experiments inside that big main chamber. Here is an example where they had a miniature version of the Cassini spacecraft. It's hard to see on this, but there are these antennae here. And what you can see right there, that is a little foil that they put on the antenna. And what they were doing is they were intentionally blasting these antennae to see if they could replicate these really weird signals that the spacecraft observed. And they were able to show that they got these really weird electrical signals that no one was really able to understand. And through doing this experiment, we were able to show that what's going on is that dust grains were actually hitting the antenna, and it creates these weird electrical spikes. So this is just some cool stuff that we can do inside of this big chamber here. But so for my PhD, I worked on this. This is the cryogenic ice target. So here's the big chamber here, and we just have this completely separate chamber that we just wheel up and then connect here at the back end. So the chamber is composed of a copper target, which is cooled by flowing liquid nitrogen. So we can get down to temperatures of like 80 Kelvin, which is really, really, really cold. We can grow or install ices of various composition then on that really cold surface. Then what we do is we blast that surface with particles coming from the dust beam, which again are traveling at like several kilometers a second. And this violent impact process rips apart the surface material and creates ions, so things that have a charge on them. Because they have a charge, we can use an electric field to accelerate them. And again, they then move down this detector tube, or this flight tube, towards a detector. And again, the lightweight particles travel a lot faster than the heavy ones. So if you look at the signal on our detector, after some time, we get a spike when the light particles hit, and then sometime later we get a spike when the heavier particles hit. So we're going to be looking at a lot of these squiggly lines now. This is the type of data we produce in this. It's called time of flight mass spectrometry. And the important thing is that each time you see one of these vertical lines, one of these squiggly lines, That means there's a population of ions with a mass that is related to the amount of time it took for them to show up. So again, we can use this to measure the chemistry by measuring something about the time and thus the mass. So here's an example spectrum. This is just plain water. This is what just water looks like in our system. You have time here on the x-axis, but again, we can convert that then into a mass axis because we know something about how time relates to the mass. Then we can use that to start identifying what these different lines are. These are what we call the characteristic water cluster sequence, or the water backbone. So there is mass 18, that's H2O. This is what we call protonated water, so water plus a hydrogen or plus a protein. So it's mass 19. And in a lot of these water cluster sequences, this is how water actually likes to ionize. It doesn't like to ionize by itself, it instead likes to just grab a positive charge from somewhere else and ionize that way. So this is the kind of structure that we see whenever we have water ice in the system. And then right there, that's our iron line right there, that 56 Fe. So that's iron, that's the actual dust particle that's coming in and striking the water surface right here. So then what we did is we created this airbrushing system where we could spray an ice across the surface, or spray water droplets across the surface, a cold substrate. And by doing this, what we can do is we can create a very evenly distributed surface of ice mixed with the organics, like something like amino acids like histidine. There's actually a tremendous amount of work that went into this. A lot of my PhD was not actually doing a lot of this other stuff, it was just figuring out that this is the way that we should have done this the whole time. We spent literally years going down rabbit holes, doing things that were just not really working until we figured out what the correct solution was. This is the solution. We actually just did this with like a paint thrower, like like an artist's paint thing or something you'd use to spray paint a car or whatever. We put that into we custom made some stuff to put it into like a nitrogen, case, I'm blanking on the phrase right now, the word, but big box that we filled with nitrogen. And then we just did this with a paint thrower in this environment. Yeah, that was the most important thing that I figured out for my PhD, was actually just figuring out to do that. Anyways, so then we can spray this thing across and we get this even distribution of organics. So the trouble is, like, if you tried to do this, like say you took a glass of salt water, right, and you put it in your freezer, what would happen is that the water would freeze, and as it does, it would extrude the salt grains, right? So you'd get a chunk of pure ice with a layer of pure salt on top of it. The same thing would happen if you tried to do this with, like, say, histidine or these other organics. So really, a big part was just figuring out, again, this is how you do it. You spray it across, the droplets freeze instantly on contact, and thus the organics or the salts don't have time to move beyond the scale of these droplets. They have to freeze in place, and so you get an even distribution, a homogeneous distribution across the ice surface. This is a glove box. That's the word I was looking for. This is the nitrogen glove box. This is a big chamber, antechamber here where we put our sample in, and then we have all kinds of liquid nitrogen and stuff in there. Just as an aside, we actually had to install a bunch of like safety exhaust ports because we were worried that when you dunk something really hot into liquid nitrogen, it produces a tremendous amount of gas, and we were worried about this thing like blowing up. So we just put a bunch of like safety release valves all over this thing, so that way it would just start shooting out, when it got to too high of a pressure. So the other thing we can do, though, is we can then pump the water out. So this is a cold surface. When we put this into vacuum, we can then let this slowly come up to a room temperature and then pump the water out to create a surface of just the pure histidine, the pure amino acid spread across the surface. So that way we can do very carefully controlled surfaces, or controlled studies, where we have one, which is just the amino acid, and another where we have ice as well. So, and then what we can also do is then grow water ice back on top of it by cooling it back down and doing more vapor deposition. So we did two experiments. One, where we did this, we pumped the water out, and we have then a surface of pure histidine. Then another one, where we deposited 60 nanometers of water ice layer on top of it. And so with this, we can do this direct comparison between one that is just the amino acid and one that has a little bit of water ice protecting it. So let's color code these. I'm using purple for the amino acid. So let's do that. Experiment 1, which is just the amino acid, is purple or pink. And then experiment 2, we'll do aqua blue for a water ice layer. So then, this is the kind of data. Again, a bunch of squiggly lines. We have mass here on the x-axis. This is our histidine line. So this is the amino acid that we were studying. But then you see we have a couple of other lines here. These ones with the pink dotted lines here. So this is mass 110, and then this is 81, 82, and 83. And we call these the characteristic breakup products of histidine, because every time we see histidine, we see these fragmentation products. If you see, this is just something that shows up virtually all of the time. So these are fragments. So then, now what we're going to do is we are going to step up through the different velocity bins. So this is the lowest velocity we studied, where we have 3 to 4 kilometer a second impactors. And what we're going to do is we're going to jump through these, and what you're going to see is all of these other lines are really going to take off and become much, much larger, while this line is actually going to slowly get smaller and smaller, meaning that there's a lot more fragmentation going on. You're no longer seeing the parent molecule. Everything is now starting to break up. So here we are at 3 to 4 kilometers a second, 4 to 5, 5 to 6. And there we are at 14 to 15 kilometers a second, which is not the fastest that we took data for. It's just the fastest that I bothered to analyze the data for, because it takes a lot of time and effort. The interesting thing, though, is that here, this mass 110, which is the dominant breakup product, you can see it's now off the scales. It's off the charts, whereas the histidine line is still over here. So really, there's a tremendous amount of fragmentation going on here. So now let's do the same thing with our blue layer with the 60 nanometers of water ice. First, we're going to note these different lines. These is our characteristic water cluster sequence, right? So water 1, water 2, and so on and so forth. So now let's do the same thing. Here we're at 3 to 4 kilometers a second, 4 to 5. And there we are at 14 to 15 kilometers a second. So from this, you can see again the other lines have risen up dramatically, but an important thing is right here. This mass 110 line is actually still significantly smaller than the original parent histidine molecule here, showing that the water ice layers are protecting this and reducing the rates of fragmentation. It's a lot more obvious when you look at these side by side. Again, look at just how this thing is blowing up compared to this one, where it's just really dramatically reduced. So then, the other thing, hold on, what did I? Okay, yeah. So now, what we can do is let's try to quantify this. Like, what I just said is very hand wavy. How do we actually measure this and get numbers out of this? What we can do is we can figure out which of these lines are really useful for us to use as fragments, so we can compare them directly from experiment to experiment. These lines are where the water cluster sequence is. These are kind of tough because we can't really say anything about them in the other one, because they could be fragments, they could be water ice layers, right? Or they could be water clusters. These lines right here, these are associated with the iron impactor. These are a couple of other lines that are associated with sodium, which is just a contaminant that shows up all over the place, and also potassium. And that means then you get lines like these, which have these pink lines here, or more like here, these green lines, throwing them all over. These are the different lines that we can use then. Anything that has a green or a pink line is something that we know is a fragment product. It's not something else that we expect to be in the system. So what we can do then is we can measure the amount of ions, the amount of molecules that are in each of these different fragment lines, and take the ratio of all of those compared to the original parent molecule here. So we can measure how much of the ions do we see as a fragment as opposed to how much do we see of the original parent molecule. And one thing else I wanted to say is just if we look at the NIST data, so this is from National Institute of Standards of Technology. Here what they do is they intentionally blast histidine with electrons, high energy electrons, to produce ionization, but they're intentionally inducing fragmentation. They're deliberately trying to fragment it. One of the interesting things is that the dominant lines we see, 81, 82, and 83, and then 110, are also their dominant lines. So this is showing us something that's kind of comforting here. It means that even if fragmentation happens, it's not necessarily the worst thing in the world. So imagine we go to this thing, right? You see mass line 156 for histidine. The trouble is that there's a couple different ways you could make something at mass 156. It could be something other than histidine. But because we know that 110, 81, 82, and 83 are characteristic fragment products, if you see 156 and 110 and 81, 82, and 83, that is now a fingerprint for histidine. It's a dead ringer. It really it would boggle the mind that it's anything else. So the point of this is that fragmentation may not necessarily be the worst thing in the world. It can actually sometimes be your friend, unlike this microphone. Yeah, all right. So anyways, if we overlay our data with this, this is what we see here. And so again, you can see there's this nice matching overlay here. It shows again that this makes sense. This is what we expect it to be. In other words, we can use these existing databases to help us identify what the original parent molecule was, even in the event of fragmentation. So it can sometimes be useful. So then, anyways, again, now let's take the ratio of all of these different fragment products and compare it to the amount in the original parent molecule. You get a plot that looks like this. So here you have your velocity bins on the x-axis. So, and then on the y-axis you have these different ratios. So the higher up we go, the more fragmentation we're seeing. Again, we have pink for the bare histidine, blue for the water ice layer. You see that things down here are actually pretty flat. Nothing's really changing until you get to around this part right here, around 7 kilometers a second. So we did these linear fits, which we found to be the simplest and best. They were just the best fits to the data. Remember, though, we wanted to find a speed limit. So there's clearly two different regions here. There's clearly this high slope region, and then there's this flatter region down here. Well, one way you can quantify this and just say where is the, what is the magic number, what number do we pick, is where do these two lines intersect? Oh, which is right there. So we have the lower one at 6.1 kilometers a second for just the histidine, and then the one that's protected by water ice is like 8.5. So somewhere in between there, take your pick, call it 7 kilometers a second. That's your speed limit. Beyond that, if you go significantly faster than that, you're going to just start to see an awful lot more fragmentation. So the conclusions are that the speed limit is between 6 and 8 kilometers a second. Below 6 kilometers a second, fragmentation is kept pretty minimal. And so when you send your dust analyzers or your flying trash cans to icy ocean worlds like moons, just be careful about going above 6 or 7 kilometers a second. So where do we go from here? Well, we can't reach for the stars. They're just too far away. But we can reach for the ocean worlds. And the thing is that we talked about only a couple of these tonight, but there's really an awful lot. There's Europa, of course. There's Enceladus. There's also Titan, which is its own ball of insanity. It's like the weirdest place outside of Earth in our own solar system. It's really cool. There's Ganymede. There's Callisto. There's Triton, which is a moon way the hell out at Neptune. Right. There's Pluto. Even Pluto, which is way out at the far reaches of the solar system, right? Like it's at the edges of the Kuiper belt. Even Pluto, there's reason to believe, might actually have a little bit of an icy ocean world. There's been some papers that look at that. And that's even Pluto, which is definitely, absolutely, 100% not even a real planet. But even that might have... Right. Anyways, so... the point is that there's an awful lot of these places. They're all really cool. In fact, there's even more than I have time to really cover. There are so many of these places. So I'm going to do something a little bit tacky, and I'm going to end on a Carl Sagan quote. What Carl Sagan once said is that somewhere, something incredible is waiting to be known. What I would say is that I think there's something incredible waiting to be known at every single one of these. They're all really fantastic. They're all really cool. And so, there's something incredible waiting to be known at all of these different places. But exactly what? Well, we won't know until we go. So let's go.
Check, check. Oh, this one's back on. Maybe it was a wire thing. Is this one on? This one's also on. Just be careful, I guess. Thank you. That was great. I hate to take your quote away, but yeah, text your questions if you have any. I got one. How does so much water accumulate on a small moon near Jupiter, but not on so many others? Or yeah, but not on so many others.
That is a very good question, and you'd have to ask someone who does geophysics or planetary science that I don't do. I apologize, I don't know the answer.
Fair. Can you make an argument for caring about Mimas?
No. I don't, I guess what I would say is, like really, I'm all about astrobiology. That's really, I guess, maybe just I'll take a step back and say, so there's the Outer Planetary Assessment Group, OPAG, and it's kind of interesting when you go to these meetings when they're talking about, what should we go and study, because there's, a lot of fighting. OPAG has to study a lot of different things in the solar system, because there's a lot of things in the outer planets. There's a lot of things you could go study, and so there's always kind of an interesting balance of who wants to go study what. And there's a lot of people who always want to go to the ice giants like Neptune and Uranus and whatever. And I'm like, what's the point, man? Let's go to Europa and Enceladus. That's where if there's life, that's probably where it is. To me, I'm just that's where we should go. They're the two best. That and Titan are the really cool places. Fragmentation can sometimes be your friend. What I'd really say, so I should say the Europa Clipper is going to have a typical flyby velocity of 5 kilometers a second. So it's safe. There's not going to be a ton of fragmentation for this. However, what you could do is when you're in your extended mission, when you're able to do more goofy stuff because you already have completed your primary objectives and you're kind of just now getting to do cool stuff, maybe what you want to do is you want to have a couple of flybys where you intentionally come by and you just go flying by at like 12 kilometers a second, and you intentionally shatter everything. Because again, sometimes fragmentation can be your friend. So you can really just explore two different parts of the parameter space, if you will, if you fly by at a bunch of different velocities. And so it's really more, I think, for like the extended mission and for like what kind of stuff would you do going forward.
How many squiggly lines did you look at during your PhD?
Really the ones that you just saw. So again, we spent an awful lot of time just looking at, trying to figure out how to best do this. Eventually there should be follow-on studies with, studying a lot more stuff like mixtures, not just a single amino acid. If you recall from that plot where the simple ones are produced the most, what you can use as a biosignature is not any one of these amino acids. It's understanding how much of the complex ones are there relative to the simple ones, right? Because you had that more flat distribution. So really what you want to do is you want to study not just one or two, you want to study a bunch of them and see how do you get really ionization efficiencies, so that way you could, when you get this data for real, you could compare it to something and say quantitatively how much of these amino acids are there and how much of the complex ones are there relative to the simple ones. That's a really cool thing that someone should do. Unfortunately, I went to a different university and I don't have access to this thing anymore. So yeah, someone else should do it. Maybe one of you can do it. It's going to be cool.
Does the critical breakup velocity have implications for the possibility of life?
I don't. Well, okay, so that's kind of a big question. So there's a lot of question as to where, like, the prebiotic chemistry for Earth came from, right? Like, could have come from comets, from a variety of different impactors. So there's that. There have been studies where they've looked at, like, asteroids, and if they have, like, organic chemistry or perhaps even, like, like life, if this impacts the Earth, could something survive? So you could say it might have something there, but really, especially for a lot of those tend to be really big impactors, like asteroids, right? Like kilometer scale things. And I just think that this experiment no longer really applies. This is about the really tiny stuff where you have this complete and total ionization of this dust grain. I think it's a different kind of thing for these larger impactors.
Thank you. If you have any questions that I didn't get to, Zach will be around. He'll be happy to answer any questions. Don't be weird. And then let's thank our speaker once again. We're gonna take a quick break. We'll be back in like 5 minutes. Quick break, quick potty break. Don't bombard the bar. Yeah, we'll be back in about 5 minutes for Astronomy in the News. Next, astronomy news anchors from the UTSA Astronomy Club and else.
Hello, everyone, and welcome to this evening's edition of Astronomy News. I'm Caleb Guimar, once again.
Jasmine Singh.
And we are giving you the astronomy news for this evening. So, first and foremost, what you can expect to see in the skies of April. Go outside mid-month around 10 o'clock p.m. Bear in mind that it is now going toward the season where the nights are shorter, the days are longer, so you will have to go out a little later in the evening in order to get a really nice dark nighttime sky. But go out there around about 10 o'clock in the evening, and this is the sky that you will generally be able to see, at least on the moonless nights of the month. You are sitting under a springtime sky for the most part. Yes, we have now exited the winter season. We are now in spring. All of these wintertime constellations over here, like Orion, the Mighty Hunter, Gemini, the Twins, Aldebaran, Taurus Bull with Aldebaran in it there, they are all setting over on the western horizon. So nonetheless, we are saying goodbye to them, but hello to this region of the sky here with the constellations of spring. One of these shapes is very familiar. Can anyone tell me what that is? Big Dipper, yep. Now, that is, of course, an asterism. It's part of the much larger constellation of Ursa Major, which is Latin for the Great Bear. Follow the arc of the bear, and it leads to the star Arcturus. That's part of this kite-shaped constellation called Boötes, the herdsman. And then spike down to Spica. Spica is this kind of bright blue star. This is part of the constellation of Virgo. It's supposed to make the outline of a woman in the sky. Follow the front two stars down to the bright star Regulus. That forms the heart of Leo the lion. The backwards question mark shape, the heart of the lion, and then that makes the head the main chest, heart of the lion. And then, of course, the triangle-shaped back end here of Leo. So that is indeed Leo the lion in the sky. If you follow the front two stars of the Dipper on up, they lead to the one and only North Star Polaris. And then, of course, the Little Dipper or Little Bear right there. So, a few things to look out for in this springtime sky. Obviously, find Mars. It's still up there, just right next to the stars Pollux and Castor. They're in Gemini right now. And Jupiter is setting over toward the west. So if you go outside at night, look toward the west, find about the brightest thing that's there, with maybe the exception of the star Sirius. That is the planet Jupiter in the sky. If you look at Jupiter with a fairly powerful pair of binoculars, you will be able to see the little moons going around Jupiter, all right? So do make sure you get a good look at that. For those of you with binoculars, we are looking at a rather barren part of the sky right now in terms of really close star clusters and star-forming nebula. We're looking out of the plane of our galaxy as we enter the springtime season. But you can find a few good deep sky objects, particularly M3. So remember, following the arc of the Dipper to Arcturus, look about 2/3 of the way in between, just a little off center, and you will find this globular star cluster M3, home of an unusual number of variable stars for a globular star cluster, about 23,000 light years away. So you're looking at it as it appeared about 23,000 years ago. For those of you with telescopes, use the opportunity to take a tour of the multiple stars visible in the sky. Find Castor right there. It's a double star. Algeba, that star right there in Leo. Mizar up there in the Big Dipper. And last but not least, Cor Caroli, which means the heart of Charles, probably named after King Charles I, who was executed after the English Civil War. I'll let you guys look up more of that fascinating, riveting, and bloody history later. So, indeed, there's the sky tonight. So I'll go ahead and hand it off to Jasmine for the news stories. There you go.
Hello. All right, so quick news stories. So first of all, Sphere X just captured its first images. Now you may be thinking, this doesn't look that pretty. Well, it's a test. It's test images. We're testing to see if all the instruments are working well and ready to operate, which I think they did a good job. So SphereX, it launched very recently. It's designed to study the universe's origin and evolution, and it's going to end up surveying the entire sky in infrared light, collecting data on over 300 million galaxies and 100 million stars. So you can see we've got some good data here in all the different wavelengths, so depending on the color. So really exciting stuff. Oh, wrong way. All right, and then next we have James Webb news. James Webb actually spotted a really unusual old galaxy called that big, all right, we went the wrong way, sorry. This really long name right here. It's actually only seen 330 million years after the Big Bang, so it's a really, really old galaxy. And it's been giving off a type of light that should have been blocked by neutral hydrogen gas filling the early universe, which might be a little complicated, but it somehow cleared that gas around it much earlier than expected, so basically astronomers don't know what's going on here, and they're trying to figure that out using James Webb, which I think is really exciting. I think that's the whole point of this. Now, I'm not going to get too much into chemistry and everything. Oops, wrong way. All right, this one I'm actually really excited about. We have seen auroras on Neptune for the first time with the help of James Webb. So as you can see, this is Hubble data, and then this is that same data with Hubble and Webb, and you can see the very bright auroras here on Neptune. So astronomers had actually previously seen hints of auroral activity on Neptune from Voyager 2, but they weren't really sure. They weren't sure if they could confirm that or not. They hadn't had images or anything like that. So now, finally, with Webb's near IR sensitivity, it's been possible to see these auroras on Neptune, which I think is really exciting. So, yeah, Neptune enjoyers out there. Wrong way. Okay.
All right, and so we'll go ahead and wrap up with a couple of things here. First, the events coming up for the month of April. In terms of the UTSA Observatory / San Antonio League of Sidewalk Astronomers, we have First Friday observing this Friday at the Flown Observatory, at the Curtis Flown Jr. Observatory, Flown Science Building, UTSA. Weather permitting, of course. We've been having some shaky weather recently, so don't miss out on that, though, if the weather is nice. We have a really fun time up there showing what's visible in the sky through the telescopes there. We have a second such observing the second Friday of the month, April 11th. Don't miss out on that if the weather's nice. And then my personal favorite's going out to South Llano River State Park, probably about an hour and 45 minutes northwest of here, on April 26th, Saturday, April 26th. Beautiful skies out there. Please, if you've never been out there, do join us. It's really an awesome time. For SAAA, San Antonio Astronomical Association, every Wednesday at sunset, there's observing out Raymond Rimkus Park with them, so keep them in mind as well. And at Guadalupe River State Park, there will be an observing on April 5th with SAAA. And then Scobie Planetarium, they'll have planetarium shows on the 4th, 11th, and 25th. The doors open at 6 o'clock p.m. There will not be shows on Good Friday, obviously. And then observing featuring SAAA on the first Friday. Tune in to NASA TV on the evening of April 7th, the early morning, like midnight, April 8th. And there is a crew launching to the space station from Baikonur Cosmodrome in Kazakhstan, including American astronaut Johnny Soon. So anyway, make sure to tune into that if you get the chance. And then a few images to close out. This is the lunar eclipse as viewed from the moon. So it's technically a solar eclipse there on the moon. That's from the Blue Ghost 1 lander very recently. You can go and describe the rest.
Yeah, I'm not going to go too much into detail because I frankly don't think the PowerPoint does these images justice. Please go online and look at these in detail and zoom into them, especially this one. This is one of my favorite James Webb images. I say that about every new James Webb images that come out, but it continues to just blow my mind with these new images. So yeah, this is This is kind of an ejecta coming out of a young star, and you can see, actually, we caught a galaxy right there, which is really, really cool. I mean, there's a bunch of galaxies, but that one's, very visible. And then we have a new image of the Lagoon Nebula from Hubble, which is one of my favorite nebulas. We have several different images, but I really like that one with the blue stars. And then we have another image of the Small Magellanic Cloud from Hubble. So there you go. Enjoy these pretty images.
And thank you very much. That is Astronomy News.
Yeah, I'll take that. Next up, we have Dr. Alan Whittington. Born, raised, and educated in the UK, Alan started out researching how granites formed in the Himalaya. After a couple years in France, he moved to the US and started focusing on magma that makes it to the surface, i.e. volcanoes. Then he started studying lava on other planets, which is often similar, but sometimes very different to our own. He has been at UTSA since 2019, where he is the PI of the Heat and Mass Transfer and Experimental Rheology, or the Hamster Lab, little s, applying materials science techniques to understanding the lava flows and their hazards. I don't have enough hands. And what is your drinking word?
All right, I think we're going to do magma.
Oh, geez. Like we said, drink responsibly. Down is next.
Down is, okay, great.
And then if a video doesn't start, you might have to click down again.
Okay, yeah, that's likely to be an issue. All right, good evening, everybody. Thank you. I'm going to start by talking to you a little bit about volcanoes, because you might not all be very familiar with volcanoes. And then we're going to go on to do space volcanoes. You may have noticed that anything you can think of, if you put the word space in front of it, instantly becomes cooler. So, all right, also, I like show and tell. I'm a very tactile learner, something I think a lot of geologists are somehow. So we have some samples to hand around. So each of these is an actual piece of lava that came out of a volcano. The first one, how many of you play Minecraft ever and are willing to admit it in public? Okay, all right. So this first one is, obsidian, volcanic glass. The second one is kind of, it's a very easy to grab shape. It's a little bit like a misshapen football. This is a volcanic bomb. This is from Craters of the Moon in Idaho. It's kind of a slightly spirally shaped. This would have been molten when it came out of the volcano, flew through the air, spinning around to mold it to this shape, and then had solidified before it landed. Otherwise, it would have turned into what we call a cowpat bomb, which is a very different shape. Anyway, so volcanic bomb that's made of basaltic lava. Here is lava that is definitely younger than anybody I can see in this room. This came from Kilauea in 2018, so it's not yet 7 years old. It's pretty bubbly, relatively light. And then finally, pumice, which is incredibly light. This is a rhyolitic, very silica-rich lava, but the main thing about this is it's very full of bubbles, which is why it weighs almost nothing. And interestingly, this is the same composition as the obsidian, which you will, as you will feel, is much, much, much denser. Thank you. Okay, so some of these are going to be, oh yeah, right. So lava, yes. If you cool it slowly, it'll crystallize. If you cool it quickly, you'll get glass. Bubbles are important. Okay, so, we'll talk through all of these. All right, so we'll start in the top left. That is a lava flow on a volcano in Guatemala called Pacaya. And actually, the top left, and bottom right are all the same lava flow on this one volcano in Guatemala. Not all on the same day, but just a couple of days apart. The one on the top right, this is lava from Hawaii. So the piece of lava from Hawaii that's going around would have looked very much like this, except you can see we're kind of scooping it with the hammer. get the crust out of the way. We've got that still very, very hot, very gloopy lava. And that's all our drinking water for the day. We are miles from the truck. Anyway, all right, so as we look at the lava from Guatemala again, that's near the vent. The vent is actually just out of view. If you see, can we restart them? Oh, okay, go up. Oh. All right, well, imagine that there's motion happening. So there are some black dots on this flow up here. There's a couple. Those black dots are actually boulders that fell on top of the lava flow and are being carried along with it. In the bottom left, you'll see the lava has basically stopped moving. It's mostly cooled down. You can still see that the surface is now no longer glowing, but inside it's still glowing and bits fall off. And then at the bottom right, you will see me hammering open a piece of lava that just fell off the flow. All right, so thank you. Okay, so boulder rafted on this lava flow coming down the side of the volcano. It's fairly steep. Here we have the hot, fresh, gloopy lava behind that crust. Notice these flows are really, really thin. So it's still really hot. But it's actually much worse standing in front of this one in the bottom left because you're standing in front of a wall of lava that's like taller than we were. And you can see here it's slowing down. It's much more viscous. It's actually what I study. I'm not going to talk about it much in this talk, but I study the rheology of lava. This is a piece of lava that fell off the edge of the flow, and that's me whacking it with a hammer. So now it's brittle, right? It's no longer squishy. I hit it with the hammer. You'll notice I rather foolishly stood on it to hold it still while I was hammering it. That was not... Anyway. All right. So hot lava, fluid. Cooler lava, pretty rigid. There's also differences with the amount of crystals. More crystals is more rigid. And then there's differences in different lava composition as well. All right, so what makes lava come out of the ground is mostly bubbles. So bubbles is what really forces magma to the surface. And then when it comes out of the ground, of course, we call it lava. And so we can have these are lovely bursting gas bubbles. This is a very fluid lava with big bubbles that are rising through the lava. But as they rise, they expand and help to push it all up to the surface. All right, so that is something like the picture on the right, where we have big bubbles that rise faster than the lava and drive these lava fountains. A lot of other volcanoes, of course, explode, produce massive amounts of volcanic ash. That's what happens when you get sticky lava and the bubbles can't escape. They're trapped inside it. And then the only thing that can happen as they get up towards the surface is that they just break the lava into fragments of volcanic ash. Volcanic ash is just tiny hot rocks. Actually, a lot of it is volcanic glass. This is why volcanic ash is so bad for you. It is like tiny micron-sized little daggers and will go right down into your lungs, slice you up, and then form concrete afterwards. So don't breathe it. And it's really hot. It'll burn you. So anyway, as an example of the lava that came out of an explosive eruption, that pumice, right, which is full of bubbles, those are bubbles that couldn't escape, and then we got an explosion. All right, this is one of my favorite outcrops, just lots and lots and lots of bubbles and a basalt from New Mexico. All right. Oh yeah, so, right, remember, when it's underground, we call it magma. Geologists are much less hung up about this terminology than you would think, actually. We use both somewhat interchangeably. Anyway, all right. So normally when we think of a volcano, we might think of the rivers of fire. There's obviously a long exposure image of Hawaii on the left. That's just a screen grab from a CNN video from Iceland a few months ago on the right. So that's a fissure eruption where a big crack opened up and lava comes up along the entire length of the crack. And when a lot of this fluid lava comes out, the lava piles up, and we get something called a shield volcano. So a great example of this, Mauna Loa on Hawaii. And it's easy to remember, Mauna Loa is lower than Mauna Kea, which is the one with the telescopes on it. Anyway, so this is taken from Mauna Kea, looking at Mauna Loa. And that rises more than 13,000 feet above sea level, more than 4,000 meters tall. So why does Mauna Loa or Mauna Kea sometimes get called the largest mountain on Earth? Because it didn't start at sea level. So these volcanoes in the ocean, places like Réunion and the Hawaiian Islands and the Azores and so on, they start on the sea floor about 5 kilometers below sea level. So this gives more of the full picture. So from sea level to the summit, the Hawaiian volcanoes are actually more than 9 kilometers. Everest is just 8,848 meters above sea level. Sea level is a totally arbitrary and random place to measure the height of any mountain from anyway, and it changes through Earth history. So, but at volcanoes, you can actually measure the height quite precisely because all volcanoes are built on a pre-existing surface. So what we call the edifice is the pile of lava that made up the volcano. So you can actually measure their height pretty precisely. All right, so are there larger volcanoes in the solar system? Why, yes, there are. So this is the Tharsis province on Mars, which is itself already this big plateau of thick crust and very high standing crust, which split, cracked open to produce the Valles Marineris right here. And then there are these various volcanoes, the three on the dome, and then Olympus Mons just off to the side. And Olympus Mons is the biggest of the three. It rises 15 kilometers. The edifice is 15 kilometers high, but it's already on a dome. So actually, it's about 24 kilometers above the mean Martian land surface. Anyway, how big is it? So we were just talking about Mauna Loa and Mauna Kea, which of course are 2 of the 5 volcanoes that make up the island of Hawaii. Olympus Mons is as big as the entire Hawaiian Islands, about the same size as Arizona or Missouri, whichever you prefer. All right, so we can produce these shield volcanoes. We can also, if we just have lots and lots of lava pouring out, a lot of it is just going to cover whatever landscape is there in lava plains. And so here's a couple of examples at the top. This is from the 1783 eruption of Laki in Iceland. This eruption, which has been credited mostly by volcanologists with triggering the French Revolution, because the eruption of Laki was very large. It led to climate effects and widespread crop failure in Northern Europe, and hence starving peasants, revolt, and so on. There was cake in there somewhere, but anyway. All right. And then this is more lava plains, kind of. That's actually a photo of Mauna Loa. Again, Mauna Loa, a shield volcano, has a pretty low slope, so a lot of it looks just kind of flattish. All right, so we get lava plains in other places on the solar system, including all of the terrestrial planets, so Mercury, Venus, Earth, Mars. This is an image of Venus. So when we look at images of Venus, we have to remember that it's covered in that very, very thick haze, and you can't take pictures of Venus with a regular camera, but you can get images with radar. So what we have here is radar images, and basically bright means rough, and dark means smooth. Anyway, so this is a volcanic flow field, on Venus. Oh, thank you. So a little bit similar but larger than the ones we just saw in Iceland, for example. All right, on a plane, if you have fluids flowing, like lava flows, the lava will often form channels. And if it's a relatively low gradient, just like a river, the lava will start to meander and form a meandering channel. So the one on the left is, again, a radar image of Venus, with this, almost looks like it's starting to form an oxbow lake or something right there. The one in the top right is Schroeter's Valley on the moon, which is really cool because it has a little rill, this little intestine-looking thing here, inside a bigger rill, which is just like on Earth when we get a floodplain, and then you have the meandering channel that is constantly migrating within the floodplain. If you've ever lived anywhere up the Mississippi, Missouri rivers, you'll be familiar with that. And if you haven't, well done. Anyway, all right. I can say that. I spent 17 years in Missouri. All right, so, so here's more sinuous rills. This is on Venus. Those are a couple of kilometers wide, tens to hundreds of kilometers long. What's inside the channel appears to be more or less the same as what's outside the channel. If you look at a river channel, then what you have in the riverbed might be quite different to what is, on either side, because it's stuff that was brought from somewhere else and deposited in the river channel. Here, it all looks pretty similar. It's a lava plain cut by a lava flow. Basically, it's all lava. So, what about smaller features? So, cinder cones are very cute little volcanoes. The one very famous one is Sunset Crater in northern Arizona, just outside Flagstaff. Famous partly for its spectacular coloring. So the way cinder cones form is when you have lava that just like comes thrown out of the ground, out of a single vent, and it just piles up, basically. And rarely do they get more than 400 meters high. What does that look like when it's actually forming, I hear you ask? Well, it looks something like this. Now, if you're very, very confident in exactly how far the lava will be thrown out of the vent, you could set up a camera right on the edge without even a helmet. Anyway, this was the 1980s. It was a wild time. All right. So what about cinder cones elsewhere? There are cinder cones on the moon. This is the Marius Hills in the Oceanus Procellarum, which is a big cluster. Hopefully you can tell. You can see also impact craters, of course. We can see some rills and fragments of rills. But all of these little blobs, smudges, these are all cinder cones. It actually shows up much better on the geologic map, of course. Geologists love to get our coloring pencils out. And that is what the geologic map looks like of that same area. Anyway. All right, cinder cones on Venus. So these are a little bigger. They're about 2 kilometers in diameter and a couple hundred meters high. And you can see the same morphology. That would not look out of place on the moon or on the Earth. The similar thing formed in a similar way. There are some smaller features that look a little bit similar to this. And they form by lava-water interaction. So this is a lava flow in Iceland where the lava flowed over wet, boggy ground, of which there is quite a lot in Iceland. So along comes the lava flow, and periodically, and like actually pretty frequently, as you can tell from all these mounds, it'll heat up the water in the peat bog underneath it, and at some point that will start to boil and turn to steam. It'll expand thousands of times very rapidly, and it'll make this little explosion and a little crater. And they look something like this, person for scale. So these are not big features at all. And they're called pseudo-craters, so they're not a place where lava came out of the ground. The lava came sideways along the ground, but it did. There were all these explosions under the lava flow. And we found things that look like that, a little bigger, in this case, on Mars. So this is more good evidence that there used to be quite a bit of water on the surface of Mars. Not only wet water, but also frozen solid water. So Iceland, again, is a great place. It's a very good Martian analog already. But up at the top, we can see these classic landscape in Iceland with these very steep-sided mountains, which are all volcanic. Here's a really good one right there. The reason they have these very steep sides is the lava comes out of the ground. Of course, before it was under the ground when it was called magma. All right, thank you. And then once it comes out of the ground, it starts melting the ice. But it can't flow sideways because the ice is really cold. Sure, lava will melt ice in the rock, paper, scissors, lava, ice game. Lava does melt ice. But the ice also quenches the lava and stops it from spreading sideways. So the next bunch of lava that comes out above the previous one, and it builds up this very steep-sided volcano until eventually it gets all the way to the surface, and you have a glacial lake and so on. Anyway, there's lots of things, lots of evidence for glaciovolcanism on Mars in the past as well. All right, on to lava domes, which happen when we have more viscous lava, like the obsidian, for example, would be a much more viscous lava. This is one called Santiaguito in Guatemala. You can see that it is producing a column of ash, a little explosion right there. But these are 4 domes that have grown from this very viscous lava that refuse to flow sideways, or at least not very much. So we have domes on the moon. So there are a couple of places where there are these lighter colored, I'm not sure how, hopefully you can see it. This is a lunar mare, which is like a field of basalt a bit lighter in color. So when you look at the moon, the light colored parts, most of them are made of anorthosite, which is essentially made almost entirely of feldspar. That's the really old part. And then the younger, darker parts, which are usually kind of circular, those are impact basins that then later got filled in with basaltic lava flows. So this is smaller scale. So this is basalt, and this is a little, we think, maybe silicic dome. There's one of the CLIPS missions on its way to the moon in a couple of years is going to land on the Gruithuisen domes, and hopefully we'll find out what they're actually made of. That just makes me think of Transformers. Anyway. So this is a lava dome on Mars, or possibly a really big sandal footprint kind of thing, I don't know. There are some freaky domes on Venus. All right, so on the left is the Anemone, 60 by 40 kilometers. On the right is the Tick, which is 66 kilometers across. It's actually it's a wonderful example of volcano-tectonic interaction, but anyway. But yeah, it's a weird looking thing. And of course, remember, these are again radar images. So bright means rough, dark means smooth, or bright can also mean a face that is reflecting directly back towards the antenna. And then my personal favorites, the pancake domes of Venus. Average 25 kilometers diameter. They're again got very steep sides. So how does something flow out very flat, but then it's got a really steep side? They're kind of curious. We think that they flow out of central vents and then just kind of on a flat surface and just spread in all directions. There are terrestrial analogs for these, which amazingly are called torta domes in Chile. And so there's a couple that we've actually been working on. These are very crystal rich, and they're also a much more viscous silicic lava. So I didn't bring a sample of that, but it looks almost like a granite. It's got so many crystals in it. Anyway, the torta domes in Chile are much, much smaller than the pancake domes on Venus. But anyway, we're going to hopefully come up with better constraints on what they might be made of. This is Lauren's job. Lauren's one of my PhD students. And of course, there are missions going to Venus to try to figure out, well, many things. But along the way, one thing they might figure out is what these domes are made of. All right, not all volcanoes are pointy. Some volcanoes are, in fact, big holes in the ground. In fact, some of the biggest volcanoes are big holes in the ground. So this is Crater Lake in Oregon, which volcanologists will always refer to as Mount Mazama. The mountain isn't there anymore, but we know there used to be one there, so we're going to call it that. Anyway, basically there was a magma chamber underneath. The magma chamber emptied during a large explosive eruption. That then reduced the pressure, and the overlying land just kind of sank down into the chamber, leaving behind this circular depression. All right, Crater Lake is maybe it's like 5 to 10 kilometers across, something like that. This one on Venus is 260 by 175 kilometers. It is absolutely enormous. Way bigger than the 2 biggest ones on Earth, which are Yellowstone and Toba in Indonesia, both of which have produced some of the largest super eruptions in Earth history. and they are dwarfed by this thing on Venus, so it's pretty exciting. All right, on to the outer solar system, and we move away a little bit from our regular silicate lava. So let's talk about Io for a little bit. Io being one of Jupiter's moons. That's its size. Texas for scale, because I know my audience. All right. It took me quite a while to get that just right. Anyway, so the observant among you will notice something interesting about Io in that picture. How many of you can spot 2 volcanic eruptions? Okay. How many of you? All right. Gold star to Tracy. All right. So, okay. So so the one that probably most of you saw is Pilan up at the top, which is spewing sulfur about 140 kilometers above the surface of Io. Without knowing about it, no reason that you would have spotted it, but this is another eruption going on that is spewing stuff, but it's right towards us, towards the camera. And that's throwing things about 75 kilometers above the surface. So what's going on with Io? So sulfur plumes, the highest ones that have been measured actually reached about 390, maybe 400 kilometers. So I know a couple of people in the room may remember homework 4 in my planetary geology class, and when they had to work out what fraction of the escape velocity of Io were these plumes being erupted at. So these things are being shot out of Io at about 1,200 meters per second, which is almost half escape velocity for Io. So it's really pretty impressive. And again, what's driving this is gases. In this case, a lot of it is probably sulfur. And that sulfur comes out of the vent as gas, but is then condensing into sulfur particles, and that's what we can see reflecting the light in the image. All right, so we've got sulfur. We also have lava volcanism on Io. A lot of these, anytime you see a dark spot like these, most of that is kind of lava and lava flows. So we've got regular basaltic magma coming out, then being lava, and then we also have the sulfur as well. All right, so not quite in order, I guess, in terms of where we are in the solar system, but anyway, we're gradually going down temperature now. So this is a dome on Ceres for which the best explanation is what's called cryovolcanism, cold volcanism. So this is Ahuna Mons, and it's interpreted as a dome of ice and salt and mud. So that's one view of it. Similar view, and then the view from above with some spectroscopic data indicating sodium carbonate. So, all right, why is this cryovolcanism and not just a glacier or a big pile of ice? So the thing about volcanism is we have to start with producing magma. We do that by partially melting the interior of the body, the moon, the planet, whatever. So if it's a partial melt of the solid body that then rises to the surface and is not stable, or basically is not stable at the surface, meaning that it's going to cool down and solidify in some way, then that's volcanism, right? If we have a geyser on Earth, it sprays water into the air. All right, then the water just flows away into the ocean. That's not really cryovolcanism, that's a geyser. But if it's a partial melt of our crust, which would be magma, then that gets to the surface. When that comes out as lava, it is going to cool and solidify. All right, so in the case of Ceres, then we're melting an icy crust, producing our cryolava, which has probably got more ice and less of the mud and sodium carbonate. There's an alternative hypothesis. Nobody has yet detected the acetic acid. Anyway. All right. Elsewhere, Europa. So this is a feature called the mitten on Europa. which is possibly a large cryovolcanic dome. It superficially resembles Obsidian Dome, which is possibly where that piece of obsidian came from, which is in California. The difference in scale is they're quite different sizes, but at least superficially it kind of resembles it. So we're not sure about that. Then there's Titan, so moon of Saturn. On the right, we have an image of SP crater in northern Arizona. So here's a cinder cone, and then a lava flow came out and spread over the desert. Also, if you tilt your head sideways, you will see Godzilla trying to tiptoe, which is quite entertaining. Anyway, I have to credit my oldest child for that observation the other day. Anyway, all right. And then on Titan, we have something that looks maybe, at least if you draw suggestive lines in the right places, it looks a bit similar. Maybe there's an actual edifice here, and this may be a cryovolcanic flow, but we really don't know. And then onto Enceladus, which we heard some about earlier. The first thing to note is Enceladus is much smaller than Europa and so on. But we do have these plumes that were detected and sampled by Cassini. One interesting question is, are these point sources, or are they in fact fissures? Remember I showed the picture of the fissure in Iceland earlier? I think, I'm not sure what the answer to that is yet, but hopefully there'll be more observations at some point. And so, with Enceladus, again, we have our ice shell, the crust. We have a molten cryo-magma ocean, which is, which we can think of as salt water. It is salty water, but for this body, it really is magma. Anyway, all right. And hopefully you'll have noticed the similarity between these cartoons showing water with gas bubbles that then burst, and we have these droplets and things that look a little bit like ash, except they're ice particles for Enceladus on the right, and then back to our picture of the silicate magma with the exploding bubbles on the left. All right, and so I answered some questions for you, but I'll be happy to take any others. Thank you.
Thank you. If anybody didn't get a chance to look at the rocks, we have them up here. I also implore you to hold a lot of the different ones in your hands. I was dumbfounded by this one. But all right, on to the questions. Why do volcanoes grow to different sizes on other planets?
All right, why are volcanoes different sizes? That's a good question. There are at least two reasons. So a simple one, which really says more about the, it is related. Gravity is one reason. So obviously for Venus, it's a very similar gravity to Earth, but if we look at the moon, the gravity is much less, and lava flows, volcanic features in general will be different thicknesses, often thicker on the moon than they would be on the Earth. But perhaps the bigger question for thinking about large volcanoes like Olympus Mons, that's not a gravity thing. That is the source of magma coming out of the mantle has essentially been under Olympus Mons, or was under it for a long time. And there's no plate tectonics on Mars, so Olympus Mons is just stuck there over the hot spot in the mantle producing the molten stuff. Whereas on Earth, if you look at Hawaii, there is also a hot spot in the mantle. There's a mantle plume. We're constantly producing molten rock, but the plate, the Pacific plate, is always moving across it. So you get a line of islands, which if you added them all up, might be really big, like Olympus Mons, but they're actually spread out into lots of volcanoes in a line. So I think that's the main reason.
Are there some space volcanoes that don't have analogs with Earth volcanoes?
The cryolava, there's no really good analog. There's a couple of places in, like Lake Superior in winter, where it will actually squirt water from the lake up through cracks in the ice, and it's not really cryovolcanism. The cryolavas we don't really have a good analog for. I had a student that did a whole PhD on that, trying to model cryolavas as if they were silicate lavas, and things are different. I mean, obviously everything's happening at a much lower temperature, but one of the main differences is the viscosity of a cryolava is really low. It'll flow very fast and in very thin sheets. But then also, when you start to crystallize, you're crystallizing water ice that it will immediately float to the surface. And that doesn't happen in a silicate lava flow. So there are weird things that will happen that we don't really understand. I'm really excited, to get more information about Europa, from upcoming missions to try to understand that better.
I was once told that some of the hills in the hill country here, such as beyond Leon Springs, used to be volcanic. Is that true?
So, kind of, yeah. So so first of all, there's the Llano area, Enchanted Rock. Enchanted Rock is a big blob of granite, so that is magma, about 1.1 billion years old, and there are other granites in the same general area. But if you go along the Volcanoes fault zone, which is basically I-35 up to Austin, and then 90 west to Uvalde and then Del Rio, there's a chain of volcanoes there that, from around, there's the late Cretaceous, so it's basically around 80 to 90 million years. If you've ever driven through Knipper, which is just this side of Uvalde, there's a quarry there, and that quarry is all this really weird lava, exceptionally dense, full of magnetite. Anyway, so yes, there were volcanoes here on the Cretaceous seafloor, actually. So I imagined, T-Rex walking along the beach and there's volcanoes erupting just offshore. It was a pretty fun time. Anyway.
Is your lab powered by running hamsters?
Graduate students, they eat more, but they follow instructions better too some of the time. Yeah.
What kind of data do we use to study space volcanoes? How do we know about their composition?
Yeah, so that's another really good question. So, it depends on where we're looking. So we can use spectroscopy as the main thing to try to identify different minerals. There's also like gamma ray and neutron spectroscopy to identify certain elements. But for Io, for example, that's a fascinating one. All we have is estimated temperatures. And we know at what temperature different rocks will melt and produce different kinds of lava. But there's a big debate at the moment. Is Io producing lava similar to what we would get at Hawaii, a basalt at maybe 1200 degrees C? Or is it producing a lava called komatiite, which on Earth mostly formed only in the Archean, the first half of Earth history, when the interior of the Earth was much hotter. And these magmas may have formed at about 1600 degrees C as kind of the upper range of the estimates. So for that one, we're just going on the temperature, and we don't even have a really good handle on the temperature. So,
is it hard to handle lava? Is it
to handle?
What is that like, being right there, just hammering away?
It's sometimes it's too hot to handle. We have really big gloves in our lab, so we always, in the lab, we handle it in crucibles. Anybody, any thoughts on what material we might have in the lab that melts at a higher temperature than lava, which is what you need in a crucible to handle lava? Thank goodness it's not asbestos, but that's... So actually, it's platinum, which is, so if we have a bad day in the lab and somebody drops a crucible, not only do we have lava on the floor, but we've also just damaged the platinum crucible. So that's why we spend a lot of time training students not to drop the crucible on the floor. Anyway, so actually the two places in those videos where you saw where we're sampling, we all got like pretty kind of burned from that. And but even worse, I think, is like the wall where it was moving really slowly, because there, it's like 2 meters high and glowing and incandescent. It's just a lot of heat. It's really astonishing how much heat comes off those things. So.
Let's thank our speaker once again. All right, we're going to take a quick break. We'll say 10 minutes. But if you're out, you're out. Thanks for coming. It was great having you. We're going to have trivia after this. And if you want to stick around for trivia, I'm going to come around with trivia sheets and pens. Just raise your hand here in a moment, and I'll come around to you. And also, we have the rocks up here if you didn't get to see them. I found it. Double check. Everybody has a score sheet. Everybody has a working pen. Speak now or forever hold your peace. All right, let's get it started. Question 1. Ancient astronomy and Ptolemy's geocentric solar system, planetary retrogrades could be accounted for by introducing this phenomena, which was even used by Tycho Brahe. It is no longer needed in the heliocentric model. Is it A, deferent, B, epicycle, C, the equant, or D, the gravitas? I will remind you, normal trivia rules apply, so if you have an answer, don't yell it out. If you don't have an answer, don't yell it out. Mark the letter only, please. That will make grading go by a lot faster. We have a more than usual number of trivia players today. But yeah. Caleb, thoughts on Ptolemy? You like him? You don't like him? You agree with him?
Well, no, of course, I mean, not anymore, but I mean, at the time, he was a very brilliant astronomer, you know, I mean, given the limited resources, you know what I mean?
So you're not a fan of the geocentric model?
Oh, no. None of that geocentric stuff. No, maybe we could mix it up. Maybe we could make it like a Mars-centric.
Yeah.
But yeah, you know,
Why geocentric?
yeah, you're right, you know, I mean... You know, actually, technically, Brahe's model was a little like that. It was like a half geo, half heliocentric thing. It was really weird, but yeah.
I don't think I can picture that one off the top of my head, but yeah.
Yeah.
All right, we can come back. We can come back and repeat questions if needed at the end. But we're going to move on to question 2.
Okay, so question 2, Papal State and Astronomy. In October 1582, Pope Gregory XIII dropped his new hit single, the Gregorian calendar, that remains widely used in today's Western world. Which calendar preceded it? A, the Hebrew calendar, B, the Coptic calendar, C, the Ptolemaic calendar, or D, the Julian calendar? Yeah, I know. I can never get that silent P thing right. Yeah.
The P's always silent.
Say again?
The P's always silent.
Oh, yeah.
Astronomers know this. Well, I hope.
You know, this actually reminds me of a planetarium show that I put on at the Cosmosphere. You know? Yeah, it was called Star of Bethlehem.
Yeah.
It was talking about the different astronomical events that could have been what the wise men were said to observe. Yeah. And it was really interesting. Went into all the changes in the calendar over time and everything.
Yeah.
It's really cool. Yeah.
It's interesting to think about like ancient Chinese.
Say again?
It's interesting to think about like ancient Chinese events with like converting and going back and thinking of like what happened. Like, no, I was watching a video, but like there's a tapestry that shows Halley's Comet.
Yes, the Bayeux Tapestry.
Yes.
The Bayeux Tapestry.
Yeah, and that's like from like 1,000.
Oh,
or something like that.
Yeah.
Like year 1,000.
Yep. Well, I think the events it depicts are in 1066 because what depicts is William of Normandy invading Britain. I think the tapestry was made somewhat later. I think it was more like in the 1500s at some point in time.
Okay.
So I'll have to look that up again. But
old.
Yeah, old. Yeah. I haven't been over there to Europe to see any of this stuff, and I'd love to see a lot of that.
Yeah.
You know, it'd be really fascinating. Yeah.
All right, question 3. Long journey. What is the estimated time of flight for a spacecraft launch in a Hohmann transfer orbit whose destination is Uranus? Is it A, 5 years, B, 10 years, C, 20 years, D, 40 years, or E, 80 years? Shinting? Oh, a couple of us are in Shinting's class, and we literally calculated Hohmann transfer orbit time, so this is Sam's idea of normal trivia. Once again, that is sam.hart@sweary.org if you have any qualms.
Yeah. You know, actually, it may be a fair question. Do you want me to drop a hint?
Not with the answer.
It's not with
Or
the
not
answer.
with the hint either.
It's not with the answer. Think of Kepler's laws.
I don't know how applicable that hint is, but we'll take it. We'll take it.
Yeah, yeah.
The ones who know, and I don't think that was what that doesn't add. But yeah. I see what you're saying.
Yeah, yeah. Think about it for a moment. Yep.
Yeah.
Yeah, yeah, yeah.
By the way, the Hohmann transfer orbit to Uranus would never happen. That would never happen. That would be.
Well, now you're giving them too much of a hint, probably.
It doesn't matter which one you pick. It would.
Well, yeah. I mean, I don't know. I mean, if it were like, well, okay. I'm not going to say anything. But yeah.
No matter which answer you pick, if you did a Hohmann transfer orbit, that is that amount of time with expending fuel. Like, that would be crazy. You would need a rocket ship like the size of, I don't even know, like the Empire State Building. Like, that would be a big rocket with a lot of fuel. We've said too much. Next question.
All right, so question 4. Io in mythology. The Greek woman Io, after whom Jupiter's moon is named, is a priestess of this Greek goddess, who is the goddess of marriage, women, and family. Is it A, Aphrodite, B, Athena, C, Calypso, D, Gaia, or E, Hera?
A priestess of this Greek goddess.
Yeah, this one's a little tougher, actually. Yeah. Remember, that's sam.hart@swery.org. Yeah.
Any qualms? Reach out to him. He's watching right now because he texted me, so he's watching. I inadvertently learned a lot about Greek mythology just learning about the solar system.
Yeah.
And also, I guess, Roman mythology. Which is
Yeah,
just
there's a
Greek
little bit
mythology,
Roman
but
in
just
there because
Latin.
it depends on which names are used and everything, but
Yeah.
they're very similar. I mean,
Yeah.
yeah.
Everybody good? All right. Question 5. Stars and Stripes Forever. According to me, Sam, unable to be fact-checked, how many U.S. state flags display stars? I don't. Is it A, 4, B, 9, C, 18, D, 30, or E, all 51? P.S. The sun is a star. Also, Puerto Rico counts.
Yeah.
Apparently not.
Yeah,
Apparently
yeah.
Puerto Rico counts. I don't know if that's a hint or not. If Puerto Rico counts, does Guam count? Like, I don't.
Yeah, technically, if D.C. had a flag, I guess that would count. And if Guam, you're right. Say again? Yeah. Well,
Well,
actually,
I guess
let's
in
see. Hold on.
Sam's-
Because,
In
let's see.
Sam's definition,
I think it'd be 55, actually, but yeah.
according to Sam, I think we're only including Puerto Rico. So that's why the all 51 is there.
Yeah.
Yeah, Guam out.
Again,
Samoa out,
the
Virgin
email
Islands
is sam.hart@swery.org.
Also, it says like according to me, like I don't know. You could just look up all 51 apparently flags and just be like,
Did you want to do anything?
Oh, I mean, we already know the answer.
Oh, okay. Well, no, I meant was did you want to So whatever you, if you really
I'll
want,
do the last one.
you'll do the last.
Could you do me a favor? Actually, could you, in the Discord, could you write down Sam's? Everybody make their guess, because I would guess. Question 6, volcanoes are cool. Which volcanic eruption is the largest by volume? A, Mount Tambora. B, Krakatoa. C, Hungatonga. D, Mount St. Helens. Or E, El Chichon. Sometimes I think Sam just wants me to say weird things. So this is the largest by volume.
Yeah.
With the volcanoes are cool thing, I was expecting like a cryovolcanism kind of thing, but no. Mount Tambora, Krakatoa, Hungatonga. Alan, off the top of your head, do you know what this is? What this image is? Panatubo? Which one? Listen, Sam gave the answers, and this is Sam's trivia. So, and also, like you say, Yellowstone. Could we measure it? I don't know. Like the earliest one is 1815, and they measured that somehow without satellite imagery. All right, does anybody need a question repeated? Hold your finger up if you need a question repeated. No one? Everybody's good? All right, we're moving on to the bonus. Jasmine, you want to do the bonus?
Yeah. All right, time for our bonus question. So, this NASA spacecraft holds the record for the longest operating satellite. Hint, it is still operating. And the bonus is, in what year was it launched? Closest answer gets credit, so I recommend putting something down.
This one is interesting.
Yeah, actually. Well, it should be easy,
Yes, but
but it's when you get into the bonus it
Yeah.
gets a little tricky. Yeah.
I know. Yeah. Oh,
Yes. No. And this goes in the bonus section. Please, in the bonus section, write the name and then the year underneath so we can grade easily. Thank you very much. When you are done, please bring your answer sheet and your pen. Please, we need those pens. This is not a for-profit institution, so we need those pens. Please and thank you. Is that everybody? Does anybody have a trivia sheet still? Please raise your hand if you do. All right, hold tight. Winners, and I'll hold up the prizes.
All right, I think we are ready to make the big announcements. So we'll start out with the answers to each question, and then we will announce who the winners are.
All right. Answer to question 1, which was, wait, wrong way. Answer to question 1, which is about ancient astronomy and Ptolemy. It was the epicycle. This was the phenomena. The interesting about the geocentric model is that it works, especially with the epicycles, but then it gets complicated.
Yeah.
And you can move on to something better, like the heliocentric model, if you believe.
Orbits are elliptical, and that's the problem. That's a pretty big leap, yeah. So.
Oh, I'm sorry, Patrice. I just saw your text. Question 2, Caleb.
All right, so the answer to this is the Julian calendar. Yes, the Julian calendar preceded the Gregorian calendar, all right? The only problem with the Julian calendar is it does not have the proper corrections for leap years in it, okay? So, say again? Yeah.
Yeah, but which one preceded the Gregorian calendar?
Yeah.
That's,
Yeah.
once again, sam.hart@swery.org.
Yeah,
That's not.
yeah, see.
I am the messenger. Do not kill me, please, for the love of God.
Yeah. So.
And I said all astronomers know this because we use Julian date. It's like, I hate it. Wait, this camera? Wait, this camera? Sam? Don't do it again. All right. Question 3. Long journey. For a Hohmann transfer orbit to Uranus, 20 years. That's a really long time.
Yeah.
And that would... A Hohmann transfer orbit is that. Like,
You just make an elliptical orbit from the basically if you're on the opposite end of the sun, as you know the planet is that you're going to, you start out on your opposite end with that point being the minor axis of this elliptical orbit, and you shoot along that elliptical orbit to the planet that you're going to when it's on, of course, the other end of the sun there. So that distance makes the the major axis, if you will, of that
Yeah. So
that elliptical
it's
orbit.
I was gonna say it's a straight shot in the sense you go in space. Straight is not straight, but it's a straight shot. Like you don't do a gravity assist. You don't go to another planet to get somewhere else to save fuel. You just go straight there. And also, if it's 20 years, Uranus has to be 20 years behind where you want it to be. It's a whole thing.
Yeah.
It's a single burn, which is like, oh my God, that would,
Yeah.
20 years? No. Anyways, pathology. Anybody? Anybody?
Oh, okay. For number 4, the answer was Hera. So.
Oh. I got that one wrong in my head.
The goddess, yeah, the goddess of marriage, women, and family. Yeah.
Question 5. 30. There are 30 flags. Not
According
fact
to
checked
Sam.
by Sam.
According to
Sam, that have stars on their flag. I know one flag that has stars.
The USA, and Texas.
The USA. Well, yeah. And then question 6.
Yes. It was Mount Tambora in 1815.
Alan, did you know this?
Yeah.
Yeah, of course. Okay, wait. I have a question. How do we know that's the biggest volume if it was in 1815?
So geologists spend a lot of time walking around with sticks, measuring the thickness of the ash in different places. We won't typically measure it.
Just a couple sticks and some walking. That's all it takes. And then for the oh wait. Oh. Thank you, Sam. That's interesting. Alan, do you know where Mount Tambora is? Oh, okay.
Yeah.
Makes a little more sense. And then for the bonus, this one I thought was interesting. There's like a little trick to it. You had to know, like, you gotta know. And it's Voyager 2.
Voyager 2. Yep. 77. Yep.
Now,
So-
why is it not Voyager 1?
Yep.
Voyager 2 was launched first.
Voyager 2 launched before Voyager 1.
Yep. This really
Huh?
confused the press. Just a second.
Oh.
This really
Wait, did Sam say
confused the
satellite?
press back in the 70s when they did this. The reason why Voyager 2 was launched before Voyager 1 is because Voyager 2's trajectory was built such that it could pass Uranus and Neptune. With that trajectory, it would exit the solar system after Voyager 1 being launched later, okay? Voyager 1 was configured so it would just go by Jupiter, Saturn, and exit the solar system. So even though Voyager 2 was the first one launched, Voyager 1 would outpace Voyager 2 eventually and be the first one out of the solar system, hence the Voyager 1. And actually, I should mention also that Voyager 1 was the first one to reach Jupiter and Saturn before Voyager 2 did, taking that trajectory.
Do you know off the top of your head, it was like what, like a month? Voyager 2 was launched before Voyager 1?
Yeah, it's something along that line. Yeah,
Like
one
not a
was
long time.
Yeah, one was August, one was September. Yeah.
So,
Oh, well,
all right. Samuel.hart@swiri.org.
Samuel.hart at Swir-
I will be honest. I will be candid. Everybody answered relatively correctly. So everybody interpreted, I guess you could say incorrectly, but they knew what we were talking about, I guess. I understand the qualm. Samuel.hart@swiri.org. Camera's right there. Talk to him right there.
Yeah, looking at the answer sheets, I will assure you that the ambiguity on this would not have improved anyone's chances of winning under the circumstances. If everybody would have achieved like 3 out of 5 or 4 out of 5 on the regular questions, or however many, well, actually I think it's 6, right? 6. So like 5 out of 6 or 6 out of 6 in regular questions, this might have been a major stumbling block. But looking at the sheets, I can assure everyone you didn't get cheated out of anything. Okay, so
Caleb said it, not me. I will say I think the most creative answer, given what we were told, is the Hubble. Is Hubble older than the space station?
yeah, Hubble's older than the space station. Hubble was launched in '90. The space station was launched, at least first module, in 1998.
First module.
Now, I think there though are possibly some Earth orbiting satellites for other purposes that are older than Hubble that may still be operating. I'm going to have to think about that for a bit. Yeah. I know for a long time, a few of the Pioneer probes that were for solar observing, like Pioneers 6, 7, 8, and 9, some of those actually held the record for the longest operating spacecraft for a very long time until Voyager finally surpassed that record. So, no, it decayed. It decayed from orbit. Yeah. The oldest satellite still in orbit, non-functional obviously, but the oldest one is Vanguard 1, which was launched in I think it was 1958 was when it was launched, and it's still orbiting out there. So I would really like to, if I had a lot of money, I'd like to fund a project to go out and pluck that thing out of the sky, bring it down to a museum down here. I think that'd be real. Yeah, which one? I know which one I'd choose, but no, I think I'd make a trade. Give the official one to the Smithsonian, and their backup goes to the Cosmosphere. But yeah. There's other things I wouldn't be as generous about, but too long of an explanation. But
All right, so we're going to go ahead and announce the winners. So in third place, we have Broken Lamp. And you're going to get these 2024 Night Sky Almanacs. I know they're 2024, but there's still a lot of useful information. The information is accurate, so come on up. Oh, and they get those stickers. Oh, you get stickers too. Bepi Colombo stickers. Yeah. And stickers. Yeah, and in second place we have Fishing Without a License. That's a great name. You get this James Webb Expanding the Frontiers of Space Astronomy poster and some stickers. Yeah, decide who's going to get them. All right, the moment you've all been waiting for. First place, we have Moon Magma.
there we
this
are. All right.
Celestron swag, this hat, a frisbee, and some Juno stickers.
They had one in the bag.
Yeah, so divide amongst yourself.
It glows in the dark. So
Oh yeah, it glows in the dark. Yay.
All right, everybody. That concludes our program for the night. Thank you for coming out. We want to thank Blue Star. We want to thank our servers. We want to thank UTSA. If you want to sign up for our email list, we have a QR code right here. I am the one that adds you to the list, so I will know if you do or do not. And then follow us on social media. We have all of them. Pick your poison, I guess. And also thanks to Southwest Research. A lot of our materials come from them, and we store our stuff there. So thank you, everybody. See you in a month. I don't know what day the first Wednesday is, but May 7th. Sam was ahead of it. May 7th. All right.
Yep.
See you,
Once
everybody.
again, thank you, everyone. Yep. Have a great evening.